Our next speaker today is Leslie Burnett. Leslie is the Chief Medical Officer for Genome One. Genome One is part of the Garvan Institute of Medical Research, and Leslie has pioneered the development of many pathology and genetics initiatives. As John mentioned previously, genomics is part of where things are going. I'd like you all to join with me in welcoming Leslie to the stage.
Thank you very much. The previous speaker mentioned that genomics is going to solve everything, and perhaps if what it doesn't, then proteomics will look after it. A slight exaggeration, but genomics is certainly in its ascendancy. When I started back at medical school some long time ago, my colleagues went in different branches, and the extroverted amongst them and went into surgery, and the debonair and suave joined your college as physicians, and it was left for the pathologists to be the backroom boffins who ended up going into the basement of the hospitals. And we stayed there for many years. And those who happened to go into the area of genetics have suddenly realised that through a combination of medicine, science and IT, our time in the sun has suddenly appeared. Over the years, what is medicine has changed because our knowledge of science has changed. We have a better understanding of the basis of disease. We used to know it was caused by bad humours, and if we refined and drilled, we could let those bad humours out. And with technology advances, we went into the era of leeches and cupping, and that was thought to be the ultimate. But today it's all about evidence-based and the science underpinning pathogenesis and medicine. And through genomics, we suddenly have an explosion of knowledge, enriching our scientific understanding of disease and rapidly making its way through translation into a clinical practice. My task today is to, in a few minutes, show you how genetics and genomics and the difference between them are going to impact on your practice and the practice of your patients, not just in medicine, but in broader society. I'll give you some examples of the very rapid changes that are occurring, and perhaps give you a glimpse on what's going to be happening over the next 2 or 3 years. So firstly, genetics and genomics. Genetics hasn't changed, it's still the study of heredity, and the laboratory testing of genetics has changed a little bit. I'll give you some examples later, but it's still about testing using a laboratory technique one gene at a time. But the technology has allowed us to move from that to genomes, the study of all the genes in an organism, and it's actually now almost as easy to do all 20,000 genes as it in the human, in fact in all organisms, as to do one gene. And we've reached a tipping point that within the next 2 years or so it'll actually be cheaper to do all 20,000 genes than it will be to do one gene. And I'll give you some examples there. So the way in which we practice, the way in which you will investigate conditions, and the way in which the patient's journey through their life when they come into contact with you and with other members of the health profession will soon change, because the information that will be there will be quite different, and the paradigm of having a pathology test every time you see the patient will change, because once you've got the genome for life. Of the different types of conditions, I'll be talking mainly about germline, those that are inherited from your parents and passed on to your children. You've got them at birth, and they will, together with environment and lifestyle, modify your health. A little bit about somatic, and briefly at the end, where the changes that occur throughout your life due to random changes, errors in the DNA replication, or X-rays, cosmic rays, or whatever that is causing random chance alterations in your DNA are going to cause diseases such as cancer. And there are many other forms of genetic disorders, but I won't be going into them. They're the two main ones which are going to perhaps be in the renaissance for the next 2 or 3 years. So patients don't present to you with a genetic problem or with a diagnosis. Patients present to you because they've got aches and pains or illnesses that refer to you. And so it is that you'll see your patient the way you always have, and you'll construct in your mind through taking a history and examination, a series of hypotheses about what the patient might have, and then you'll investigate those conditions, and from that you'll come up with a working diagnosis, which you'll proceed to investigate the patient. So this is the clinical method. It works. You'll tend to do things ad seriatim, one investigation or a small number of investigations at a time, and depending on the information, you'll either confirm the diagnosis, exclude the diagnosis, or go back and repeat the cycle again. But the disruptive driver of change has been the cost of gene sequencing. The first human genome sequenced all 3.2 billion nucleotides in the haplogenome for, by coincidence, $3.2 billion US. By the turn of the century, the price had already come down to $100 million, and so it was still as a very expensive laboratory research tool, till we come through to about 8 years ago, where the concept of next generation sequencing or massively parallel sequencing made its way from the research laboratories to the first of the clinical laboratories. And Moore's law, the familiar doubling of speed or power or halving of cost every 18 months, has been broken by this technology. We're now into a hyper-exponential falling in cost and increase in power. And again, I'll show you examples where currently around 2016, the cost of a human genome is about $1,000 in reagents, more in labour. And with the next generation of equipment, which is just reaching Australia over the last month or two, that will go down probably half an order of magnitude. So it'll be down to several $100s for the chemical sequencing alone. So the way in which genetic investigations will be undertaken will change. Let me walk you through the range, some of which you're probably already using, and showing you how these will evolve. We start off with the single gene tests, which have been around now for some 20, 25 years. They're still available. They're still ideal when you have a single condition to investigate, like cystic fibrosis or hemochromatosis sickle cell disease. You're looking for a genetic change, a mutation, that's now non-PC, a genetic variant in a single gene, and it's either there or it's not there. You'll hit or miss, but it's one gene at a time, and that testing is still the most widely used form of testing in pathology, and it'll probably still be the cheapest when you know exactly what you're looking for. But the problem is very few genes are linked exclusively to just one condition, and very few of those is only going to be one variant that you look for. So it soon became clear that for clinical presentations, there were often a collection of genes, so-called a panel of genes. And so instead of doing them one by one, why not gather those genes that are always gathered together, like birds flocking together, do all the genes that are associated with this particular condition. And so when you get a referral, test them all. And panels typically are in the size of 20 to 200 genes. It's uncommon to have a bigger collection, partly because the conditions are not understood at that level, and partly because it's technically very demanding to optimise a laboratory assay so it works equally well for more than 200 different genes and many variants within each gene. The price of these is also coming down, but it's somewhere around typically the $500, $1,000, $1,500 mark, and they're very, very good. The one problem with them is that it takes about a year to do a laboratory validation of a complex gene panel, and just when you get it right, you pick up the latest issue of the journal and you open up and your heart jumps when you see there's been a major discovery and yet another gene has been associated with the disorder that you're investigating. And you get excited for a moment until you realise through gritted teeth that that means you're going to have to reconstruct and revalidate your panel for another 3 or 6 months' work, and you know by the time you've revalidated, there'll be another gene discovered. So that's why different laboratories always differ slightly. This laboratory's got 210 genes, that's got 185, this has got 100. They're all about the same, but there are different cycles, different points in the cycle of adding and revalidating. And sometimes a gene is added because it's discovered, sometimes it has to be removed because what looked to be promising 12 or 18 months ago has turned out to be perhaps no longer associated with that particular condition. Well, what about going to the ultimate gene panel? There's only 20,000 genes. Build a gene panel of all 20,000 genes. Then you won't go out of date. And indeed, that's what the whole exome is. The exome is a gene panel of all the coding genes. The way in which these are constructed is you take the whole genome and with molecular tags or baits, you pull out all the coding regions, all the exons, and you sequence them all simultaneously. A high degree of expertise is required for this. There's about half a dozen laboratories in the country that are able to do whole exome sequencing, and the diagnostic rate jumps considerably. most studies, depends on the particular referral condition, but you get about 20 to 40% diagnostic yield from a whole exome. But wait, there's more. Why stop at just the coding region? We know the coding region of the genome is only 1% of the genome. We don't know what most of the other 99% is, but everyone knows that at some point we will know what that is, so why don't you go and do the whole lot in one go, the whole genome? This way, using informatic techniques, you can pull out the coding region, you can filter down to an exome, you can apply the exome technology now, but as new discoveries are made in the future, you can go back and reanalyse the genome without having to resequence it. And so it is that whole genome sequencing occurs. And also another advantage of whole genome sequencing, because you're not baiting or pulling out particular exons, there is no predetermined hypothesis. You have a much more hypothesis-neutral signal. So a genome is said to make an exome better than a whole exome is. And indeed, the diagnostic rate is about twice, about 40 to 60% on the same range of conditions as an exome. The drawback is that it is more expensive. And the studies are underway whether genomes or exomes. I think with some oversimplification, everyone believes the genome will eventually be there, but at the moment the cost benefit may be hovering somewhere between the exome and the genome. This is just illustrating that in a range of conditions, the genome is slightly higher than the exome, and then our own modest contribution for the polycystic kidney disease, where we find that the genome is remarkably successful with almost a 90% yield. So the pros and cons of doing exome or genome size analyses, well, the pros are it's got the maximum power, maximum diagnostic yield, it finds everything, it's the best value, lowest cost per gene, but if you don't actually want all the genes, perhaps there may be a cheaper technology available. And the downside is that, well, it finds everything, it even finds things you're not wanting to find. So just as if you've got a sore shoulder and you have an x-ray and you discover you have a mass in the chest, so it is that you may go in looking for one gene, but you find you've got a significant variant in another gene. And people differ in their wanting to know. So the issue of incidental findings or secondary findings or additional findings, they're almost the same meaning, though slightly different terms are applied in the American, European, Australian literature, is when you look for A and you end up finding B. And so a large part of the work that we do in the laboratory is applying bioinformatic filters or blinkers, so we make sure that we only look for the things that either you or the patient have asked us to look for, and we deliberately blind ourselves to those things, blind ourselves where possible, to those things that we don't have permission to examine. I make a personal observation that medicine and I guess radiology, imaging, is very accustomed to the concept of incidental findings, but genetics is obsessed by it. I always find it interesting that the first thing you do in a consultation is you talk about the things you don't want to find before you talk about the things that you do want to find. And that view differs between countries and societies. So let me just take you on a brief photo tour of what's required to sequence a genome. By way of disclosure, I'm employed by this organisation, so at the same time it's easier for me to get photos of them. So the Kinghorn Centre for Clinical Genomics is a part of the Garvan Institute here in Darlinghurst, only 20 minutes walk from here. And commencing in 2012, 2013, it had always been, I don't know what I did there, always been active in genomics, but the decision was made to make a major push into clinical human genomics. As a result of a large charitable donation, the world's first clinical diagnostic sequencer was purchased here, predating even America, and we were the second site in the world to be accredited, being beaten just by 2 weeks by Hudson Alpha in Alabama. The building is almost a purpose-built DNA sequencing facility. It's 11 stories high, 2 below the ground level where the computers are and the 9 above it, and 1/3 of the building is involved in genomic sequencing. It looks a little bit like Hogwarts Manor. It has strange stairways at different angles, and the room floors change as you walk between levels, but it's an exhilarating place to be, where there are about 400 people within the building, all working on different elements of genomics, genetics, or clinical oncology. The first machines were purchased 4 years ago, the HiSeq 10X. They come in packets of 10, and I'll show you in a moment what they look like. This is a room full of them, and this is one analyzer. There are 10 of them in the room. This is impishly described as the world's most expensive bar fridge. This is it is a bar fridge. It's a refrigerator that contains all the chemicals. This is the robotics that takes the sample test tubes. I'll show you what they look like. And this is the camera and the fluorescent lasers that will take the imaging. And underneath there's a small set of workstations. And when these machines are running full speed, of the 10, 9 of them are always in use. One of them is being either serviced or loaded or unloaded, and the entire network infrastructure of the building is occupied capturing the data when those machines are flowing out. So each machine will analyse, it takes 3 days to analyse a genome. It analyses 8 samples simultaneously, times 9 machines, times 24/7. When you work it all out, it's about 16,000, 17,000 genomes a year, or 1 genome every 30 minutes. So that's its throughput. But of course it takes longer than that to interpret that. The machines are very IT intensive, and the key to it is a modified glass slide, which looks like that, where there are special chemical hooks that hook on to fragments of the DNA. There are 8 lanes there, so we can either analyse 8 patients at once, or 1 patient 8 times over if you want greater detail, or you can even mix and match different patients together, because each fragment of every patient has got a molecular barcode added to it. A group of 40 over the years have been built up, so it takes 40 people to drive one of these machines. And if you look at the composition of them, we've got a small group of clinicians, but the largest group is actually the bioinformaticians. So we have IT staff from a range of backgrounds, from science, from statistics, from banking, from finance, any form of big data. And it's really a meeting of minds between the biologists, the information technologists, and the clinicians as we apply our skills in very defined, codified ways to solve the problem. And I'll show you in a moment again how we put that together. And finally, just over 18 months ago, we submitted ourselves to NATA and the College of Pathologists for the standard pathology accreditation, and that's the first and still the only accreditation certificate in the country. And the Garvan split off this thing called Genome 1, which is basically just the clinical diagnostic arm of the Garvan. But that was 2 years ago. Things have changed in 18 months. If I draw your attention, the first machines arrived in 2014. That's an eternity in the world of genetics and genomics. This is the new kid on the block. The previous one was the world's most expensive bar fridge. This is the world's most expensive top-loading washing machine. It costs over $1 million, and the way in which it works is that that's the speed of the old machines. This one is 3 or 4 times faster, and it also is capable of mixing genomes and exomes, and there have already been 8 of these sold in the country. We think 5 or 6 of these for clinical diagnostics. There's going to be an enormous number of genomes sequenced over the next 2 or 3 years, or else there's going to be an awful lot of second-hand top-loading washing machines coming on the market in about 18 months. So you've got a machine that sequences DNA. What do you do with it? Well, name any part of the human experience and you can sequence a genome. You can sequence the genome before you get pregnant. You can sequence the circulating DNA in the pregnant mother at birth, children. You can solve many pediatric disorders. You can start with rare disease diagnosis. I'll give you some examples of pharmacogenomics. I'll give you some examples of cancer. And you can go through, even do the molecular autopsy, find out why the person dropped dead after having the marathon run. You can look for the cardiac arrhythmia, that a genetic variant that was there they didn't know about. So rare disease, inherited disease is the initial point where genomics was applied. Preventive health management and preventive health care is the next most exciting area. I'll give you some examples. And just beginning to enter, probably over the next 12 or 18 months, you'll start seeing these technologies applied in cancer diagnosis and treatment. The requesting is very simple. It's still done, even in this era, by a paper request form, then goes into the counselling process, the DNA extraction, the sequencing, the bioinformatics, and what emerges at the end is a standard pathology form in which we've taken all the information and distilled out just the gene or variant of interest. Problem is there are 6.4 billion of them, and we each differ from the next person at 1 in 1,000, so we've got 6.4 million differences from the person sitting next to you, and most of those are just going to make you look different to the person sitting next to you. They're not related to disease. And so it's a gigantic jigsaw puzzle where you're trying to build the jigsaw puzzle, but you don't actually know the picture of what you're trying to build. So the way in which it's done, we apply a series of filters. We assume that if a genetic variation is common in the population, it's unlikely to be caused by disease. If it's been described always in association and breeds true with the presence of disease, it probably is associated with disease, and so it is. We apply a series of filters, starting from 3 million haploid variants and going down to a final shortlist of 40 or 50. This is all done by high degrees of automation, and currently the final 40 or 50 are curated by hand. We think that final 40 or 50 will very soon go down to a final 4 or 5, so the algorithms will take it down to a very short list at the very end. The diagnostic yield is remarkable. I looked it up this morning for you. It's currently 56% of all the referrals to us on a wide range of different conditions. The range is from about 30 to 90%. And just as it is that the science has advanced, with each iteration, every time we make a diagnosis, we know more about what the next patient would be. So let me show you how you can apply it in daily practice. These techniques are already here, but they probably haven't quite reached large numbers of patients. Of course, environment and lifestyle will interact with genetics, but if you could add to the traditional health assessment the genome and the pharmacogenomics, this is what you would end up with, and which some of the patients already have. We firstly start with a counselling session to make sure people know what they're agreeing to. We need to know their wishes. Do I want to find out about incidental findings? Do I want my relatives to find out about it? Do I want to find out about it? So we make sure people know what they agree to before they go ahead. We then currently screen, for those who wish to have it, for a range of, this is all single gene Mendelian cancer risk conditions, a range of cardiovascular conditions, a series of rare but medically actionable important other conditions, like various anaesthetic and drug conditions, and for 22 genes that are very much involved in drug activation or drug metabolism. The testing is done through the counselling, the blood, extracting the DNA, the sequencing. We read the entire sequence, we compare the sequence to a reference genome, and we look for all the differences. And then those differences are grouped by a standard classification system into common garden variety things that are medically not important. They're not reported. The ones that are neither medically important nor medically unimportant, or which you don't have knowledge, I'll describe later, they cannot be reported, but they're not reported for screening. And the pathogenic or likely pathogenic, where there's either a 90% or a 99% confidence that these will be the cause of the patient's condition, and those ones are reported for diagnostic purposes. But wait, we can go further. Do I have too much? If this is the population, and you would like to give every member of the population a medication, the average person will respond in the average way, but of course we're not all average. So if we could find which of those people are predicted not to respond to medication, or who are predicted to have either an over-metabolizer or an under-excreter, you'll have a way of identifying those with adverse drug reactions before you actually give them the drug. So it is that we've teamed up with a group at the Mayo to produce a traffic light type report where, based on the genetic information, we classify all of the drugs in the pharmacopoeia on the basis of red light, this patient really should not be given this medication, or yellow light, this patient is predicted to have a significant interaction, consider an alternative, or green light, there is, based on current knowledge, no predicted genetic impact on the medication. So an example, if this is the lifestyle, patient's got a high cholesterol, you know that. You can, in the one test, work out whether it's an inherited form of hypercholesterolemia. You can, one step, you can work out what the medication is, and with the same medication, you can work out of which of the medications this patient is going to respond to and which are contraindicated. You see that this particular patient should not be given one statin. It's okay with the others, but there's an ideal statin predicted for this patient. The important negative issues are insurance. In Australia, we don't have a health insurance issue, but we still do have a risk-rated life insurance or income protection. There is currently a recommendation for Parliament that genetics should not be permitted to be taken into account. That recommendation hasn't yet been adopted. There are direct-to-consumer. I'm sure you already have patients who come to you, having consulted Dr. Google or 23andMe or Ancestry.com, and the issue for us, our concern is that there's no health profession involved, and it is currently illegal to provide that testing from within Australia, but the internet is a global village. And just around the corner, we're going to move from Mendelian disorders to polygenic risk disorders. We're currently solved this bit, and we're heading our way through with probably 2 or 3 years of still having to build up the knowledge before we can apply it, but the same sort of testing will be available for the common conditions in the community. My final 2 slides, I show you where the next step is, that of personalised precision medicine. We all know that, whoops, how do I go back? This one? Yes. We all know that different mutations of different genes will produce different genetic drivers in different cancers. And we can combine that with the fact that different patients will respond to different treatments. So the trials are underway, promising so far, but still the clinical trial stage, of treating the patient not by the histology appearance of the tumour, but by the molecular abnormality of the tumour. And from that, you select the appropriate medication and then check to make sure that medication is not contraindicated in that patient. So I leave you with the thought that within your practicing lifetime, and I would suggest perhaps even within 5 years, you'll think differently about patients. They'll still present with aches and pains and symptoms and signs. You'll check their genome because, unlike a pathology test where you check it in real, once you've had your genome done, you've done it. Just on your computer or via your mobile device or over the phone, you'll ask the laboratory to reanalyse the genome that's already on file, possibly in real time, and tell you whether this patient's got any predisposition for the condition they've just turned up to see. From that, you'll be able to rule in or rule out the diagnosis without further investigation. And then shifts the question to the patient, do I want to know? And what am I going to do? So very much a patient empowerment or engagement, as we've heard from the earlier speaker. It's a wonderful time to be in medicine, very innovating, disruptive. When I started medical school, I thought this would be here, what I want to do. I thought, no, 5 years, it'll be here. It's taken a bit longer than I thought, but I would leave it with you that it's only been 40, 50 years since DNA sequence was, DNA structure was discovered. James Watson is still alive and practicing. In one human lifetime, we've gone from working out what the nature of the hereditary material is to being able to read your genome. And I would leave it with you that the 2020s will be the era of the predictive, the preventive, the personalised, and the participatory era of precision medicine.